On finding all the buttons. Okay, so this is Unit 1, Day 4, Continuity. Friday. Why is my face frozen down there? That's interesting. Try again. There we go. Okay. Continuity. Huge deal in calculus. Very important. It's a criteria for several definitions, theorems. So you have to understand continuity in order to use the things that we want to use. Visually, continuity is pretty easy. Let's draw something that's continuous. That's pretty easy. It just means, can you draw it without lifting your pencil? So that one we would say f of x is continuous for all values of x. It's continuous everywhere. I could draw it without lifting my pencil. There's no jumps, there's no holes, there's no asymptotes, nothing crazy. Simple continuity. I think I just listed all the exceptions. So one exception would be if there's a hole in the graph. So that's mostly continuous. It's just that one spot, it is not continuous. I guess we'll call these different things. We'll call this one g of x. So we would say g of x has a point discontinuity. At x equals, and we can just label that spot A. At x equals A, there's a point discontinuity. Point discontinuity has a simpler name that we've used before. A hole. That's the same thing. Why don't you just call it a hole? Well, you could, but if we're talking about continuity, we would call it a point discontinuity. Right? We could have an asymptote So that thing's definitely not continuous, right? I can't draw that without lifting my pen, hopping over the asymptote, and continuing it. So h of x has an, any guesses on what kind of discontinuity you'd call that? Infinite. That's an infinite discontinuity. At x equals a. Infinite discontinuities. What's like the pre-cal word for what's happening there? Like this example, that's a hole. This example, what have we called that before? An asymptote. So an infinite discontinuity is the same thing as a vertical asymptote. Or I guess we would say it occurs at a vertical asymptote. And then lastly, let's, I guess, call this one j of x. J of x has a, care to guess the name of that discontinuity? Jump, a jump discontinuity. At x equals a. We put a right there. I guess that's the one whose name makes the most sense because it's a jump discontinuity at a jump. So visually, continuity is pretty easy. Like if you can draw the graph without lifting your pen, it's continuous. If there's a hole, an asymptote, a jump, something that requires you to lift your pen and start again, well then it's not continuous. So visually, we like continuity. It's easy to get the concept of what's going on. All right, we're not going to talk with a partner to write your own definition because I think it would be tricky to come up with, although I hinted at it earlier on that last problem we did from yesterday's assignment, and that is so before I write anything, that one we were looking at, we talked about the left limit has to equal the right limit has to equal the function value. That's the definition of continuity. F of x is continuous at x equals a, and because it's like a formal definition and you hadn't seen one of these in a while, we'll throw the official language in here. If and only if. Remember, that means you can read the statement like forward or backwards. F is continuous at x equals a if and only if, and then I'm just going to write in the technical terms what I've said a couple times. The left limit's got to equal the right limit's got to equal the function value. Limit as x approaches a from the left. So it looks technical because there's all the little symbols we got to get right. Limit as x approaches a from the left has to equal the limit from the right. So the limit as x approaches a from the right. Left limit, right limit. If we stop there, that wouldn't be enough, because which one of those three discontinuities has a left limit equal to a right limit? G or point or hole, however you want to phrase that. That does have left limit equals right limit. So we need to have one more piece, and that is the function at A. So that's the formal looking thing. The more like informal thing that most people remember is that the left limit needs to equal the right limit needs to equal the function value. I don't have enough highlighters to star and asterisk that, box it enough. On the test, there will be at least one question that says, I think it even says use the three-step definition, so it throws you a little bit of a hint. Use the definition of continuity to discuss the continuity of whatever function at x equals 7 or whatever. And so this is what we'd be looking for. And I would need to see this. You'd have to start with that and write that out, and then evaluate each one and show that they're all equal. And as soon as one of them doesn't equal the others, it blows up and it's not continuous. And we'll do some examples. All right. If a function is not continuous at a point, we say that function has a discontinuity at x equals a. There's two kinds of discontinuity. So maybe that sounds weird because it looked like, wait a minute, we just saw three different kinds of discontinuity. But we categorize within those three. The first one, the point discontinuity, is also called a removable discontinuity. I don't know that this term is used anywhere else, but I think of it as a fixable discontinuity. Like, it's easy to fix that discontinuity. What would it take to fix that discontinuity? Fill in the hole, and you're done. So it didn't change the graph very much. Fill in the hole, and then you're continuous. But these other two, I guess if you wanted to fix them, you could, but you'd have to like get rid of the asymptote. You'd have to somehow tie those two together. Like that's not fixable. So we call those non-removable discontinuities. That's not fixable. I mean, without like radically changing the function. So a hole, that's easy enough to fix. Plug the hole and it's continuous again. The other two, you can't fix those without really changing what's going on. Let's put the technical terms on those, or the technical definition here. Removable discontinuity, also known as a hole. If, with the two F's, right? If and only if. So a removable one means they meet. So that means the left limit equals the right limit. Left limit equals right limit. But if there's a hole there, that means that doesn't equal the function value. Question, McKenna?
What does it say?
Do you remember what the two F's on if mean from geometry?
No.
Did you not use that abbreviation? If and only if. It just means that it works both directions. If this is true, then it's removable discontinuity. If it's removable discontinuity, then that statement is true. For a non-removable discontinuity, words today, lots of words. That happens. So what would where is the equation breakdown if it's not removable? If we start with this is continuous, removable meant it wasn't equal to the function. What's the trouble with this equation if it's not removable? Do you know? Because the limits aren't even equal. That means it doesn't really matter what the function's doing. So the limit from the left is not equal to the limit from the right. Then you can't fix that. It doesn't matter what the function is. Maybe say the same thing we did earlier. The removable is a hole. The non-removable is a jump or an infinite discontinuity, which is the same thing as a vertical asymptote. That's a heavy vocabulary day. And you kind of know all the words, just put them together different ways. Okay, but the most important thing on that page, because a lot of it makes sense, but the biggest one is that formal technical definition. Left limit equals right limit equals function value. Got to know that. Okay, example. State the values. So now we're going to use this. Some of these are pretty easy. State the values of x, if any, at which the function has a discontinuity. So looking at example A, where would that thing have a discontinuity? Discontinuous at, so what x value does that happen at? At x equals -2. Now that's all you have to say because that's all it asked. Some of you were giving me a little bit more information, which was fine and correct. It happens to be a hole. But that wasn't really the question. So be careful, make sure you read carefully. Now, if you answered it, if all you said was there's a hole at x equals -2, I don't know that I'd give you a full credit. Because I ask, where is it discontinuous? You're like, well, a hole is a discontinuity, but I need to make sure you answer the question. Now, if you answer it with a little more information, that's fine, but make sure you're answering the right question. So anything in the bottom would be a discontinuity. It wouldn't really matter if it's a hole or a vertical asymptote. But you're right. Let's see if we can say that briefly. Any denominator of 0 is a discontinuity. That one's a hole. You could also have a vertical asymptote. But if the question is, where is it discontinuous, you don't really care if it's a hole or a vertical asymptote. Anything that makes the bottom 0 is a problem. What about B? How would we check to see if B has a discontinuity? What about 1, Jace? To where? Both. Because if we plug it into both, if we think back to our definition, this is more work than you're going to show for this when you do this problem, but this is what sort of motivates doing this work. We're going to check the limit from the left equals the limit from the right, which means plug it into both. All right, the left limit equals the right limit. Maybe that's what we're trying to see here. So the left limit would be this guy. So 5 times 1 minus 7, that would be -2. The right limit would be this guy. 1 squared plus 3, that would be 4. And whoops, those are not equal. So it is not continuous at x equals 1. When we're talking continuity, it's important to say where we're talking about. Because this thing is continuous everywhere else. Because if you're bigger than 1, then you're on this parabola. And parabolas are continuous. If you're less than 1, you're on a line. That's continuous. So when you say continuous or not continuous, I don't want to say it always, but it almost always needs to be followed with where you're talking about. So you can say it's continuous everywhere, or you can say it's discontinuous at certain spots. Number 2, let's change this to 5x minus 1. Let's change the second one to 5x minus 1. And you'll see pretty quickly why we did that. So again, there's a potential jump at 1. Maybe that's what we notice first. So something might be going on at x equals 1. Okay. You're changing functions for sure, but maybe it's rigged so that they match up. Maybe it's like that previous one where there's a jump. The only way to tell is to check the left limit and the right limit. And see if they match up. Let's see, the left limit, that would be the smaller one. That would be 5 times 1 minus 1. That would be 4. The right limit would be the one that's bigger than 1. So that would be 1 squared plus 3. That would be 4. So that checks out. Although I haven't proven continuity yet, because continuity I need all 3 statements. So yes, the left limit equals the right limit, but the last thing I need to check is the function at 1. So which one would I plug that into, the green or the red? The green, because when we're at 1, we're still on this one. And so obviously that's going to be the same as the one we just did. But to make it official, we've got to show all 3 steps. Left limit equals right limit equals function value. 3 dots in a little triangle. We're doing all kinds of symbols here. That means therefore. You've seen that before. Therefore, f of x is continuous. You know what? I was going to say at x equals 1. That would be true, but I can say it's continuous for all x. 1 was the only place I was really worried about. X squared plus 3 is a parabola. 5x minus 1 is a line. Those are definitely continuous. This one is rigged so they match up at the same spot. Okay. 3, definitely a couple problems like that on the test. Well, like 1 and 2, but also number 3. Find the value of k that makes G continuous. So I'm going to sort of force continuity. So how would I force them to match up rather than there being a jump? Set them equal. Okay. I like that. So x squared plus 3 equals kx minus 7. That's what you said. I think there's one more step there. At 1. So I want them to be equal at 1. So equal at x equals 1. So 1 squared plus 3, k times 1 minus 7. So I'm plugging in 1. We're kind of doing the same thing we just did on the previous examples. Like plug in 1 to the left, plug in 1 to the right, and then rather checking to see if they're equal, we're now going to force them to be equal. And so if k is 11, then that forces them to be equal, which makes it continuous. So it still goes back to that idea of left limit equals right limit equals function value. Number 4, which is the following is continuous at x equals 1? Okay, Roman numeral 1. What should I do with Roman numeral 1 here? Because it looks like there's a problem at 1, but it says don't equal 1. Let's factor the top. X minus 1 over x minus 1. So we can cancel. What does that mean? What's happening at the whole at x equals 1? How do I get the y value of the whole? Plug it in for x. So there's a hole at 1, 0. That's where the hole is. The function is at 1, 1. F of 1 equals 1. So what does that mean? If the hole's at 1, 0, the function value is at 1, 1. Continuous or no? No, because if we tried to graph it, there'd be a hole at 1, 0, and the function's at 1, 1. So that is not continuous. Make sure we answer the right question here. Which of the following is continuous? So that's a no on Roman numeral 1. Because there's a hole and it's not filled in. So we got to be careful. If this had been a 0 right there, then that dot would have filled in the hole and it would have been continuous. Okay. Number 2, Roman numeral 2. Where is Roman numeral 2 discontinuous? I can't factor the top, so I'm just going to be stuck here. So what value of x would make that graph? Is there a problem? -1. So read the question carefully. Is that graph continuous at x equals 1? This thing has a discontinuity at -1. So is it continuous at 1? Yes, it is. So there's a problem, but the problem isn't what we're looking at. We're looking at 1. So this is yes, we're okay with this one. That's kind of a misleading question, because that graph is not continuous. but it is continuous at x equals 1. All right, Roman numeral 3, that's kind of the more normal one. The left limit equals the right limit. So let's plug in 1 and see what happens. Half of 2 is 1. 1 plus 1 is 2. On the other side, it's just 2. So that one checks out. That one is continuous at x equals 1. So 2 and 3. Continuity is weird, I feel like. It's super easy conceptually. Like, even in, I don't know, as soon as you know what the word continuous means, like in middle school, you could have probably told me which of those graphs is continuous. But man, there's some technical math to back up what seems like an obvious question. All right, a couple more practice problems. This one's kind of the same. What value of k makes f continuous? Well, that means plug in 1/2 and force them to be equal at 1/2. So left limit equals right limit at 1/2. This is going to be yuck. K times 1/8 minus k times 1/2 minus 1/4. And then plug in 1/2 on the other side. 32 times, let's see, 1/2 squared would be 1/4 minus 2. Ugh. So k over 8 minus k over 2 minus 1 over 4 equals 8 minus 2 is 6. What would you like to do to solve this problem next? I know what I want to do. I'm just curious if you're doing the same thing I would be doing. What's that? I'd multiply by 8. Like, you could get a common denominator on the left and multiply and like deal with the fractions. It's like, no, let's deal with the fractions by getting rid of the fractions. So let's multiply by 8. It makes things a little bit more complicated on the right, but well worth it. So negative 3k equals, add 2 to both sides, 50. So k equals negative 50/3, which is not an option. And I check last year's notes, and there's a note that, yeah, this one's messed up. So, sorry about that. K is negative 50/3. Number 6. Oh, I think this is an easier one. Infinite, non-removable, non-removable. Okay, Roman numeral 1. G has an infinite discontinuity at x equals 1. Yes or no? Yes, because at x equals 1, that's the asymptote. That's an infinite discontinuity. So statement 1 is true. Statement 2. G has a non-removable discontinuity at x equals negative 1. X equals negative 1. That's over here. Yeah, that's not removable. That's not fixable. A jump, I can't fix a jump. So statement 2 is true. Statement 3, G has a non-removable discontinuity at x equals 2. Okay, x equals 2, that's right there. That's a hole. So is statement 3 true or false? False, because that's fixable, right? I can just plug the hole in and we're good. So that's a removable discontinuity. So 1 and 2 are true, but not number 3. Which of the following has a jump discontinuity. Jump discontinuity. Okay, so that means the left limit doesn't equal the right limit for a jump. Okay. This one is kind of tricky, so we'll check F and G in a moment. Look at H. I can answer H without plugging anything in. Do you know why? How? Think about left limit, right limit. Look at how the function is defined. Which branch am I plugging it in if I want the left limit? Am I going to plug it into branch A or branch B if I'm coming from the left? So I'm a little less than 3. Plug it into A or plug it into B? A little less than 3. So if I want to plug in 2.9 or 2.99 or 2.99999 or 2.9999999, that's branch A. What if I'm plugging into, if I want to plug in something a little more than 3? 3.001. Is that branch A or branch B? That's still branch A. So I really don't even have to plug it in. Like, that at worst is a hole. There might be a hole there. Maybe. It may be filled in. But I don't care. It's definitely not a jump discontinuity. It might be a hole, but I don't even care if there's a hole, because that's not the question. It's definitely not a jump, though. Right? Because x not equal to 3, that would be graph A. At B, I don't know. There might be a hole there. There might not be, but we don't care. It's definitely not a jump. Okay, the others are easy. You're just going to plug, let's see, less than 3, that would be the left limit. Greater than 3 would be the right limit. So 3 squared minus 4 times 3 plus 1. Does that equal 1 minus 3? I don't know. 9 minus 12 plus 1. That would be negative 2. 1 minus 3 is negative 2. So, like, what does that mean? Jump or no jump? No jump. They meet up. Again, I guess I could try to figure it out. One's a parabola, and then the other one's a line. Negative slope. But they're sort of rigged to meet up at 3. No jump. So no to F and no to H. That just leaves G. I'm looking at my answer choices. Oh, I still have to do the problem because it could be B or D. But same thing. Plug in 3 to both sides. Because I'm checking the left limit and the right limit. 9 plus 6 is 15. 4 times 3 is 12. So this one is like there's a parabola, and then it starts somewhere else, and looks like that. I mean, I don't know if that's exactly what it looks like, but there's a jump. Because the left limit and the right limit are the same. Again, continuity, I always feel like is weird, because conceptually it's super easy to look at a picture and say, yep, that's continuous, or nope, it's not. But then the details of it, it gets pretty technical with the left limit equals the right limit equals the function value. I'll close by boxing that one more time in whatever color I have left to box it with. Left limit equals right limit equals function value. Okay, assignment is worksheet next, worksheet 4, wherever it went. quick look and see if there's anything. Where does it have a discontinuity? Where does it have a discontinuity? Where is it continuous? There's a K question, number 4, so you'd set them equal to each other and find K. There's a graph question. So, hey, it's only 8 questions long. At least you can maybe tell yourself it's not too bad then. Quick peek. Monday is IVT and squeeze theorem. Those go together. That's why they're on the same day. That's fairly easy. In fact, it's so easy that we have to review it at the end of the year because people forget it because it's like, anyway, it's easy. And then we'll have a day of review, and then we'll have a test. So make sure you're keeping up with stuff because everything will be due on test day. So don't let it get all backed up where you're having to do a packet's worth of stuff on Tuesday night.
Are you going to have like a physical review for each test?
Sometimes yes, sometimes no. This one, it does have a review. So you've got it in the packet already. And speaking of that, answers are already posted. So this isn't very many, but there may be a few of you who want to work ahead, or sometimes you've got a tutor that comes on a certain day and you want to start looking ahead. Like you've already got the worksheets for the packet and the answers. So if you really wanted to start, you could start the review and do some of it and check yourself and see how it looks.